Another way to find volumes using integrals of one variable is the shell method. Okay, here we'll get a volume by using shells, and it's in contrast to the disk or washer method here, because if you want a volume that you get by rotating about the y-axis, you do an integral in x, and what you basically do is break up the volume into different shells of various circumferences. Okay, so you'll get a shell of a circumference 2 pi x and a height of f of x minus g of x, and you'll multiply that by dx to get the volume of that shell, and you add all those shells together. You could also do this by rotating about the x-axis, but here you'll do an integral over y, and again, in contrast to the disk and washer method. Okay, and here your shell circumference will be 2 pi y, okay, and the height that you get will be py minus qy, and the sort of most intuitive way to get a grasp of these formulas is to actually look at a concrete example. So suppose we want to find the volume of a sphere with radius a that's been drilled out. Okay, it's been drilled symmetrically. So you just imagine this sphere, if you rotate it about the y-axis there, but missing a sort of you'll take a ball and drill it right in the center, so it's missing that area over there, that volume inside. Okay, so it's missing everything from 0 to r. Now, what's the volume of the remaining shape? Okay, that's what we're going after here, and we're going to do this using shells. Okay, so in order to get a grasp of how this problem looks and the shell method in general, so take a look over here. We'll have f is equal to square root of a squared minus x squared, because the radius of this sphere is a. Okay, and we're going to do this by shells, which looks like this, for you to get a grasp of that. If we increase and revolve around, here's what's going on, and you'll get various shells, one for each point where x is. So if I could change where x is, for example, you'll get another shell and yet another shell. Okay, and so that's where that formula 2 pi x is coming from. It's the circumference of that shell. Okay, the height of the shell is going to be the height of the pink line that you see over there, and so we'll rotate that pink line around the y-axis to get the area of that shell, and multiply by dx to get a volume, a small volume. And that's basically how the shell method works. And once we're done revolving, we'll get our sphere with a hole drilled out of it. So now that we have an intuitive grasp of what's going on, you could see that we could get a height by looking at the top part here as f of x is plus square root a squared minus x squared, and the bottom as negative square root a squared minus x squared. That's just coming from the formula for a circle. Okay, and so you'll take the positive and negative roots and to get y in terms of x for that circle. And so so how do you get a height? Your height is going to be the top function f of x minus the bottom function g of x. And again, each shell, if at some arbitrary x, has a circumference of 2 pi x. Okay, so you take that shell, you take that circumference of the shell, you multiply by the height, and what do you have? You have an area, the surface area of that shell. You multiply it by dx to make it a little bit thicker, and so you'll get a volume of that shell, and you'll add all those small volumes together. And we're integrating from x is equal to r to x is equal to a, and here's our formula here. We do a u substitution to complete this integral. After doing the u substituting and substituting back, we end up getting this formula here for the volume of that sphere with a hole drilled out of it. Okay, and it does agree with so if you'll take r equal to 0, which means you didn't drill a hole in that case, you'll get 4/3 pi a cubed. Okay, and that is the formula for the volume of a sphere. And so this is the shell method, and yet another way of finding volumes using integrals of one variable.